Lightning is a universal and striking experience, pun intended. And it's pretty incredible that everywhere in the world gets lightning. It even happens outside of our world too. So all of the Earthlings and all of the aliens know about lightning. But how much do you know about it? Like, you might be familiar with your run-of-the-mill thunderstorm lightning, but what about volcanic lightning, or supercharged lightning, or laser-guided lightning? There's so much more to lightning than you might think, which is why we made a whole video about it, even several videos. And just so we don't shock you right away, here's Michael with an intro to lightning.
Whether it's up in the sky during a thunderstorm or helping send a DeLorean back to the future, lightning is a beautiful, dangerous phenomenon. Most people picture lightning as a brilliant white strike that flashes between a cloud and the ground. But there's also lightning within clouds and between clouds. Plus, there's colored lightning and even glowing ball lightning. It's all about a buildup of electric charge and the release of that energy in a bright flash. To have a lightning strike, you first need to separate positive and negative charges within a cloud. Clouds are essentially a bunch of really small, dust-borne ice crystals and water molecules. During a storm, the air is moving around and making these particles collide. So one theory is that some negatively charged electrons from the upward-moving water molecules get transferred to the downward-moving heavier particles. This makes the bottom of the storm cloud more negatively charged and the top of the storm cloud more positively charged. And remember, like charges repel each other. So the electrons near the Earth's surface are repelled away, and the ground underneath the cloud is left with an overall positive charge. All this charge separation creates a strong electric field between the ground and the cloud. Basically, an electric field describes how much force and in what direction a positive charge would go if it were in the field, in this case, upward toward the cloud. And when the difference in charges builds up enough, the first stage of lightning begins. Most of the time, we see negative lightning. This is when the electric field grows strong enough that an invisible channel of negative charges, called a stepped leader, begins to branch toward the ground at about 50 meters per microsecond. Meanwhile, an upward-moving channel of positive charges, called a streamer, rises up. They meet with a huge, bright flash that travels up. Not to mention the heat, over 25,000 degrees Celsius, which is about 5 times hotter than the surface of the sun. Because the negatively charged electrons stream from the cloud down to the ground, it's called negative lightning. There's also the much less common positive lightning, with a net transfer of positive charge from the cloud to the ground instead. These strikes start at the top of a cloud where positive charges hang out, so they need to travel through much more air to reach the ground. So they need even more charge separation, which means the strikes can be up to 10 times stronger than negative lightning. In fact, these strikes can even break apart molecules in the atmosphere into ions, which can collide with other molecules like hydrogen and oxygen and cause photons of red light to be released. If this happens, we call them red sprites. They usually only last milliseconds and can kind of look like giant jellyfish in the sky. And if that sounds cool, there's another type of lightning called a blue jet. This lightning occurs when large amounts of positive charge stream upward in order to neutralize the charge in the cloud. The blue jets can get up to 40 kilometers high, but only last for fractions of a second. And scientists believe their blue color comes from ionized nitrogen molecules. Even weirder is ball lightning, a glowing grapefruit-sized ball of gas that lasts up to 20 seconds. But scientists aren't quite sure what causes it. One theory suggests that ball lightning is caused by ions made by a lightning strike near glass, like a window. The ions could pile up on one side of the glass and create an electric field, exciting air molecules on the other side, which would release photons and create a glow. Another theory suggests that elements in soil are to blame. In 2012, scientists in China recorded the first video of ball lightning. They monitored the light it emitted and found that it contained silicon, iron, and calcium, which are all elements found in soil. So a cloud-to-ground lightning strike might vaporize the soil's silicate compounds, which react with the surrounding atmosphere to produce a ball of light. So, the next time you're watching a thunderstorm from the warm, dry safety of your home, remember that all this lightning has a lot of physics behind it. Beautiful, dangerous physics.
All of that physics can get complicated pretty fast, so it's not the kind of thing we can observe overnight and immediately understand. Instead, scientists have spent years learning about lightning by detecting the radio waves around us. But there's still a lot about lightning that's kind of mysterious. So here are a few striking things that we still don't know about lightning.
Few natural events are as memorable as thunderstorms. Between the impossibly bright flashes of lightning and the bone-shaking rumbles of thunder, you might agree that dogs who hide under the table have the right idea. But incredibly, these powerful events are just the starter pack of electricity coming from the sky. 100 or even 1,000 times more intense than your garden variety lightning are so-called superbolts, and they have scientists pretty stumped. They're not just more powerful. Superbolts also seem to strike on totally different parts of the planet. Scientists don't know why that that happens, or even why superbolts happen at all, the answer might also help clear up some lingering mysteries about the causes of lightning itself. Over the last couple centuries, scientists have worked out a pretty detailed understanding of how a bolt of lightning comes to be. It begins with sunlight warming the planet, which heats humid air near the ground until that air starts to rise. Once humid air reaches an altitude that's cold enough for water vapor to condense into droplets and freeze into ice crystals, clouds start to form. Sometimes, as the water condenses, it keeps rising, which leads to the super tall shape of a thunderhead. All that rising and cooling makes the ice crystals bump into one another inside the cloud as they swirl around. And just like rubbing your socks on the carpet, those crystals transfer little bits of electric charge between them. After a while, enough of one type of charge builds up at the bottom of the cloud that some charge is forced into the nearby air. That kicks off a cascade of electrically charged air that eventually either reaches the ground or another cloud. Once it does, a big, bright flash of electric current travels along the path. That's a lightning bolt. But superbolts seem to break all these rules. Normal lightning tends to form in the summer over land since land heats up faster than water does, enabling humid air to rise more quickly when it starts over the land. And since warmth and humidity are both contributing factors, it's no surprise that lightning happens most commonly in the tropics. But superbolts are mostly found in the winter over the ocean off the coast of Europe, which is definitely not the setting for a tropical paradise. And yet, somehow, superbolts are hundreds of times more powerful than ordinary lightning. It's so weird that some scientists wondered if they're a statistical fluke or some kind of measurement error, but that doesn't seem to be happening. Superbolts are found by the same network of sensors that map any other kind of lightning, the same ones that find more regular lightning over land during tropical summers. Those sensors detect radio waves that spread out from a lightning bolt. The louder the radio signal, the bigger the bolt, which leaves atmospheric scientists with a pretty big puzzle without an obvious path forward. Some have proposed that pollution from all the ships passing through the English Channel helps clouds build up absurd amounts of charge before they start sparking. Or it might be that clouds with salty ocean water lose all of their charge in a bolt, while normal thunderclouds only lose some of their charge. Or it could be that there's something we fundamentally don't understand about lightning. Because although scientists have worked out the big picture for lightning pretty well, there are a lot of details that don't perfectly line up. Like the fact that the bottom of a cloud usually becomes negatively charged, but not always. Some lightning is positively charged, and some has a mix of both. Superbolts seem to break the rules here too. The more powerful a superbolt is, the more likely it is to be positively charged. So it's possible that something about the way a cloud charges has an effect on how big the lightning can get. But it's also possible that physicists are looking at the whole problem the wrong way. Experiments have shown that charge builds up in a thundercloud until the air near the cloud breaks down. But they've also shown that there's not nearly enough energy in a typical lightning bolt to make that happen. It doesn't seem like lightning should even be possible until it's somewhere in between a regular bolt and a superbolt. There are possible explanations for this, like charge building up only in specific parts of clouds, or an incoming cosmic ray from space kickstarting the process, or it could be something totally different. The existence of an even more powerful kind of lightning could be the clue scientists need to figure it out. And that's how science works sometimes. A new piece of evidence can force you to totally re-evaluate your view on the problem. Like, maybe scientists shouldn't be asking why superbolts are so big. The real question might be, how can regular lightning be so small?
Gee whiz, if all the lightning I've ever seen is little, I don't want to be around for those superbolts. It sounds like the more researchers learn about lightning, the weirder it gets. Like, even though superbolts sound pretty intense, they're nothing compared to volcanic lightning. Allow me to tell you about that terrifying combo. On the landward side, a fearful black cloud was rent by forked and quivering bursts of flame and parted to reveal great tongues of fire like flashes of lightning magnified in size. That's what Pliny the Younger, nephew of the naturalist Pliny the Elder, wrote after watching Mount Vesuvius erupt and cover the city of Pompeii with ash in 79 CE. And that line ends with the first known report of a phenomenon called volcanic lightning, where lightning streaks across the black clouds of ash and smoke above an explosive eruption, even without a thunderstorm in sight. But despite centuries of scientific study and millennia of first-hand observations, we still don't fully understand why volcanic lightning happens in the first place. Though it probably has something to do with all that ash moving through the air. Volcanic lightning generally happens during explosive eruptions that release huge ash clouds high into the atmosphere. So the most popular explanation is that all that ash somehow causes the lightning. Like we've talked about before here on SciShow, lightning in a regular thunderstorm happens when water vapor dust, and ice crystals rub against each other. Electric charges jump to some molecules more easily than others, so all that rubbing creates a huge charge imbalance, which eventually gets evened out by a sudden burst of moving charge in the form of a lightning bolt. Scientists still disagree on some of the details though, since lightning can be hard to study directly. But studying regular lightning is a piece of cake compared to studying volcanic lightning. The explosive eruptions that cause it also tend to come with noxious fumes, earthquakes, and clouds of super hot ash. But scientists and photographers are persistent. And most of those scientists studying volcanic lightning think that it happens directly because of those huge clouds of ash. The idea is that the ash rubs together in the air just like water does in a normal thundercloud, creating a similar sort of charge imbalance. And once the imbalance is big enough, you get a bolt of lightning. Laboratory experiments have reproduced the effect on a small scale, and scientists have even been able to track ash mixing as the charge builds up around it above an eruption, which seems like a pretty conclusive case that ash causes volcanic lightning. But some researchers have said that we shouldn't be so quick to jump on the ashy bandwagon. Since water causes regular lightning, they think we should take another look at the water involved in an eruption. The idea of water in a volcano might seem kind of weird at first, but enormous volumes of water can be dissolved in the molten rock that bubbles to the surface during an eruption. That water boils in the heat of the eruption, which could lead to water molecules rubbing together in volcanic clouds just like they do in normal thunderstorms. Or all that water could coat the ashy particles flying around, changing how the clouds charge up. And a growing group of scientists think that this is the primary source of volcanic lightning. Now, claiming that water causes volcanic lightning isn't new. It goes back at least to the late 1700s, when scientists knew far less about volcanoes than they do now. But research in the last couple decades has breathed new life into the idea. Many clouds leading to volcanic lightning seem to balloon out at similar altitudes as normal water-based clouds, which means that water is likely an important component of them and helps determine their behavior. On top of that, charges tend to be distributed in those clouds just like they are in normal thunderclouds. So based on the evidence we have right now, it seems like ash is the primary cause of most volcanic lightning, with water and other conditions of the atmosphere playing something of a supporting role. But like anything in science, that might change as we continue to learn more. And if you were ever to find yourself in Pliny's position, near an eruption that seems big enough to end the world, and then lightning starts flashing around you, you should probably not stop to wonder if it's ash or steam to blame. Just, get out of there. Because there have been some cases of volcanic lightning causing destruction down here on the ground, like the strikes during the eruption of Mount St. Helens in 1980 that caused forest fires. There are even a few very rare cases of volcanic lightning killing people. But even though some volcanic lightning can strike about 100 kilometers from the eruption, it usually stays much closer. So if you're close enough to a volcano that you might be hit by lightning coming straight down from the ash cloud, you probably have bigger concerns anyway. That sounds like good advice. If you're at the base of an erupting volcano, getting yourself to safety should be a higher priority than musing on the source of lightning bolts. But you can't blame the researchers for being totally awestruck by this bizarre lightning. And in my opinion, that's the best way to be struck by lightning. Much less dangerous. The thing is, if you think lightning is weird now, it's only gonna get weirder, because the climate crisis is making supercharged lightning. And here's how.
Carbon dioxide isn't just a greenhouse gas warming the planet by trapping heat in the atmosphere. According to the US National Oceanic and Atmospheric Administration, 1/3 of our estimated CO2 emissions end up in the ocean. This leads to ocean acidification, which is harmful to marine life. But ocean acidification might also trigger another phenomenon: stronger lightning strikes. Bet you didn't see that one coming. On the one hand, the ocean absorbing CO2 might seem like a good thing, because there's less of it in the atmosphere to warm the planet. But on the other hand, CO2 that dissolves in the ocean becomes carbonic acid, and the more CO2 the ocean absorbs, the more acidic the water becomes. This is bad news for corals and other shell-forming marine organisms, because they make their shells from minerals like calcium carbonate, which dissolve in acidic water. But that's not the only effect decreasing the pH of the ocean might have. We think of pH as a measure of acidity, and that's true, but on a molecular scale, pH is actually a measure of the concentration of hydrogen ions in a solution. The more hydrogen ions, the more acidic the solution is. In the case of CO2, the carbonic acid splits apart into positively charged hydrogen ions and negatively charged bicarbonate. The presence of these charged ions means the solution can also carry an electrical charge. A higher acidity, or lower number on the pH scale, means more hydrogen ions in the solution and more potential to conduct electricity. And that's a big deal, because the ocean is getting more acidic. Due to climate change, change, seawater has experienced a 0.1 unit drop in pH, which seems tiny, but the pH scale is logarithmic. A pH of 6 is 10 times more acidic than a pH of 7. So that change of 0.1 in the oceans corresponds to a 30% increase in acidity. So if climate change is potentially affecting the electrical conductivity of the ocean, could it affect lightning? This led a group of scientists to look into the idea, publishing 2 papers on the subject in 2020. Surprisingly, we don't know a lot about what happens when lightning hits the ocean, even less than we know about lightning strikes in general, because almost all lightning strikes happen on land. For something so big, covering nearly 2/3 of the Earth, oceans are only struck by about 10% of all the lightning that occurs. We used to assume that all surfaces act as perfect conductors, whether that surface is rocks, soil, or water. But while this assumption makes it easier to do calculations, it probably doesn't reflect reality perfectly. In fact, models show that when lightning does hit the ocean, it could be more intense than on land, probably because salt water is a better conductor. So, to test whether lightning could intensify as the ocean acidifies, the researchers carried out a simple experiment. They filled a beaker with seawater and placed 2 electrodes in the water about 2 centimeters apart. Then they ran power through the electrodes, forming sparks between them. Next, they changed the seawater's pH in 2 different ways. First, they added hydrochloric acid directly to the water. This is a good way to change the pH of the solution, but it doesn't reflect the real-world process of ocean acidification very well. Second, they decreased the pH by bubbling carbon dioxide into the water, which is pretty close to how ocean acidification actually works. And they found that as the water got more acidic, the spark's intensity did increase. The bubbling technique, which most closely replicates ocean acidification, made the spark twice as intense as the other method. That means ocean acidification could be making lightning stronger. In fact, the researchers claim that if ocean pH keeps decreasing according to the worst-case predictions, where CO2 emissions keep increasing unchecked, the intensity of ocean lightning strikes could increase by 30% by the end of this century. This is a definite concern for ships, oil rigs, and other ocean infrastructure. All of these structures already have some form of lightning protection, but if lightning does get more intense with climate change, these protections might need an upgrade. But it isn't just human-made structures that might be affected. Lightning strikes aren't just shocking, they're also loud. So if lightning strikes are getting stronger, animals that use sound to navigate, like whales and dolphins, might have a harder time. But maybe we shouldn't worry too much yet. Some researchers caution that while this study's method does what it's supposed to do, measuring a spark in a beaker of water might not be directly applicable to storms over the ocean. Lightning produces very large sparks, up to several hundred meters long. Sparks this big might behave very differently from small sparks generated in a controlled environment like a laboratory. Lightning is also 100 times more intense than the sparks these researchers produced, so comparing the two is a bit of a stretch. But these studies are laying the groundwork for future experiments, which hopefully will spark more research.
It's always reassuring when researchers tell us that it's not time to freak out yet. After all, if anything is going to strike people with fear, it would be climate-induced supercharged lightning. And if that still makes you worried, here's some research that might help you sleep at night. Scientists are working on ways to redirect lightning strikes, and here's how they're going to do that. Everything is cooler when it's made of lasers. This is a scientific fact. I will not be accepting any arguments. And that goes double when they're lasers that can catch lightning. For the past 270 years, lightning rods have consisted of a simple metal rod attached to the top of a building and grounded by a wire stuck in the ground. This works fine if you're just trying to protect a building or a cell tower from lightning damage. But there are other scenarios where we need lightning protection, so researchers have been trying to give this centuries-old technology a makeover for a very long time. And one team has just published a new method of guiding lightning strikes using short, intense laser pulses in the journal Nature Photonics. Worldwide, lightning wreaks havoc at large facilities like airports, power stations, and rocket launch pads, causing billions of dollars of damage and over 4,000 fatalities a year. Now, we're never going to be able to stop lightning from happening, but we can improve on the ways that we protect important infrastructure from damage. Because while it works great on the ground, a lightning rod isn't much use in the air, for example. But then again, there were no airplanes around in the 1700s when Ben Franklin was supposedly inventing it. But if we can't stop lightning, we can at least try to control where it goes. In 1965, researchers published a way of triggering lightning strikes by launching a small rocket with a trailing grounding wire into the electric fields beneath a thundercloud. Kind of like discharging static electricity before you get zapped unexpectedly. But why use rockets when you have lasers? Researchers began investigating initiating lightning with lasers in the late 1990s, and then in 1999, Japanese researchers successfully triggered 2 lightning strikes with 3 lasers. And in this new study, researchers set up a high-powered laser that fires 1,000 pulses per second near a 124-meter tall telecommunications tower on top of a mountain in Switzerland. This tower receives around 100 lightning strikes per year. They did this to test the idea that laser filamentation could be used to both trigger and guide lightning strikes using just one laser. Laser filamentation works by sending short, intense laser pulses into a medium, in this case the clouds of a thunderstorm. The intensity and short duration of the laser beam ionize the air molecules, causing them to lose an electron, and creates a narrow column of plasma, referred to as the laser filament. The air molecules around this newly formed filament get superheated and pushed away in all directions, creating a channel of electrically charged, less dense air, which is catnip for a lightning bolt. The laser filaments themselves can reach 100 meters in length, and the filamentation process can be controlled so that filaments form up to a kilometer from the laser. So this means that the laser can be used to trigger lightning to strike the filament, and it can be used to guide the lightning strikes to occur at a specific spot that's far from the infrastructure that needs protection. The researchers deployed the laser during several thunderstorms in the summer of 2021, and they were able to record 4 successful guided lightning strikes to the tower, demonstrating that the laser filamentation process worked. And while this method is still in the experimental stages, it's possible that one day a laser could be used to guide lightning away from airborne infrastructure like planes and rockets. So we might have more agency in this whole lightning situation than you thought when you clicked on this video. But you may be thinking that we've skipped over what might be the most fundamental question there is about lightning, which is what happens when it strikes us. Here's Hank to tell us just how serious it is to get struck by lightning.
Lightning strikes someplace on Earth about 100 times every second. That's 3 billion times a year. Considering that, your chances of being struck are actually amazingly low. So here in the US, where we have pretty good statistics, your chances of being struck in a single year are about 1 in 100,000, and about 1 in 3,000 over your whole lifetime. These odds can vary a lot depending on where you live and what your habits are, of course. Like if you live in Tampa and you like to play golf in July and you have no fear of storms, your odds of getting zapped are, yeah, you're stupid. But there are actually 2 different types of lightning strikes: direct and indirect. Direct is like Zeus aiming at the bullseye on the top of your head. It also occurs if you're holding on to something like a flagpole, for example, that is struck and it conducts the energy into you. Indirect strikes hit the ground and then run up your legs. More people are injured in ground strikes because the energy in them can connect to multiple people at once. So while the direct from above strike can hit a person in a crowd and leave everyone else alone, indirect strikes could kill a whole herd of cows in seconds. And yeah, a lightning strike is no joke. It's a 300 kilovolt burst of energy that can heat the air around it to 27,000 degrees Celsius, which is about 5 times hotter than the surface of the freaking sun. So, what exactly happens when the fire of 5 suns zips through your flesh and blood? Well, worst case, of course, you die. If the electrical current gets up in your skull, it can actually cook your brain like that famous egg in the anti-drug frying pan. But the most common immediate cause of death by lightning is cardiac arrest, as the shock instantly stops the strike victim's heart. Surprisingly though, 70 to 90% of lightning strike victims survive. I'm not saying they get back up and continue their game of golf unscathed, because the resulting injuries can be severe, but if you're struck, you're more likely to survive than just die there on the spot. And if you do survive, here's some of what you can expect. The force of the bolt leaving your feet could literally blow your shoes off. Meanwhile, the superheat of the strike could shred your clothing or set it on fire. And if you're wearing a lot of jewelry or, say, an underwire bra, that metal could channel the electrical current and sear your skin. The lightning bolt itself is probably going to leave deep wounds where it enters and exits your body, so you're gonna get burned. You might also end up with possibly the coolest scar on the planet. The unique physics of electrical discharge leaves branch-like marks called Lichtenberg scarring, which occur as blood vessels burst, and the bizarre fractal scars actually look like lightning. It's like getting a free souvenir tattoo. With that kind of electricity coursing through your body, you're also likely to end up with some damaged or totally fried nerves, which could lead to permanent numbness, the inability to register temperatures, or partial paralysis. Some strike survivors develop muscle twitches as well, similar to those in Parkinson's patients. Also, not technically an effect of the lightning, your eardrums might rupture from the thunder. For many strike survivors, it's actually the initial trauma that's the easiest part of the whole ordeal. The mental and physical after effects are often plentiful and bizarre. Memory loss, sleep disorders, tremors, loss of balance, intense headaches, chronic irritability, and resulting depression are all common side effects. Some of these symptoms may take months after the initial strike to manifest. Because being struck is so rare, many doctors don't know how to help their patients. This complaint, along with higher suicide rates in strike victims, has led to the formation of various lightning strike survivor support groups. Roy Sullivan holds the record for receiving the most lightning strikes. He was struck by lightning 7 times during his career in the Forest Service. But though he survived the strikes initially, they may have eventually killed him when he took his own life, likely due to depression caused by repeated shocks to his brain.
Okay, so that one ended on a bummer, but I guess 1 in 3,000 with 90% survival rates, I like those odds. So overall, lightning is super cool and weird and yeah, kinda scary, but it doesn't have to keep you up at night. And it's probably the thunder that's keeping you up anyway.